Hello everyone, I'm Haochen Yuan from Peking University, and it's a great honor to be here at EUROSYS, and thanks for the introduction by the second chair. Today I will be presenting our collaborative work with Microsoft Research alongside with Yuanqing Wang. First, let's start with the background section. The model DNN applications often exhibit a dynamic execution pattern where each input might follow different execution paths guided by control flows, loops, or branches, or switch-like. For example, a large language model generates tokens iteratively through a decoding module, with different inputs requiring varying numbers of decoding steps to produce sentences of different lengths. Similarly, in a diffusion-based image generation model, a random input tensor may need to undergo a varying number of diffusion steps to generate high-quality images. Their dynamic execution patterns are inherently efficient when we run on GPUs. Typically, to fully utilize a GPU, a DNN model needs to process multiple requests in a batch to reuse the weight data. However, the dynamic patterns are if each input sample follows different execution paths, it becomes difficult to batch the inputs together, necessitating the sequential execution, and this can easily cause the GPUs to become bottlenecked by memory access, thereby reducing the overall efficiency. And what's more, there are different main functional phases during a dynamic model inference. For example, the large language model inference contains preferring and decoding phases, and stable diffusion interface inference involves text encoding, diffusion, and decoding phases. We found that the different phases have distinct batching characteristics, and figures show that the request execution latency on each phase, which is batch latency divided by the batch size, excluding the queuing time. On a certain phase, as the batch size increases, the decreasing slope of a curve implies that the batching leads to only a marginal gain in improving the execution latency, and thus the throughput. Once the gain becomes insignificant, adding more requests to the batch no longer improves the throughput. Instead, it proportionally extends the total processing time for the batch and delaying all included requests. Thus, it is necessary to identify a critical threshold for batch size in each phase, beyond which the marginal gain becomes insignificant. Given that the slopes of different phases are distinct, we should identify a threshold specific to each phase, and batching more requests on a phase should only be considered when the batch size of the scheduled request is below its phase-based specific threshold. And what's more, since the batching characteristics of different modules are distinct, the traditional uniform batching policy and resource allocation will lead to GPU underutilization. And in model DNN serving, each request has inherent and strict requirements for latency, and the serving system should try to finish serving before the deadline. This requirement is also called service level objective. The service level objective can be a global or partial metric. For example, when we provide the text-to-image service by Stable Diffusion, the SLO could be the end-to-end generation time. But when we provide a chatbot service by large language models, the SLO consists of two partial metrics, which are time to first token, measured in prefill module, and time per output token, measured in decode module. What's more, in online serving sign, the user request arrival time is hard to predict, and achieving a best request level batching policy will be quite difficult, since we can't predict when the request will come. When it comes to a batching decision time, the server system needs to determine whether to run a current batch or wait for more requests to form a larger batch size. The existing serving system can be divided into two categories. The first category is the systems that focus on static DNNs. They do request-level scheduling, request-level batching policy, and model-level resource allocation. For example, one typical system is Clockwork at OSDI 20. These systems do not support module-level scheduling, or we say iteration-level scheduling, thus miss small batching opportunities. What's more, they will not conduct resource allocation or parallel config for different distinct modules, which will lead to a lower GPU utilization or we say lower throughput. The second category is the specialized LLM serving system. For example, the works published on OSDI like Orca, OpaServe, and DistServe. These systems focus on optimizing LLM throughput with module-level scheduling, tailored parallelism config, and disaggregated module deployment, but the optimization is only limited to the large language models. So currently, there is no integrated serving system for general dynamic DNNs and applications. So if we want to design a serving system for generate dynamic DNNs and relevant applications, there are two main challenges. Challenge one is that because of the dynamic execution path, system cannot proactively perform scheduling actions because the action path cannot be known in advance, and the batching policy degenerate into sequential execution and cause low efficiency. Challenge two is that in existing general systems, the model level uniform batching always see the resource allocation or the parallelism plans will lead to different modules heterogeneous batching performance. Next is the system overview section. In this work, we present NeuStream, a programming model and runtime system for serving deep learning workloads using stream processing. NeuStream decomposes the inference workload into modules and forms them into a streaming processing system where a request flows through. We consider that every deep learning program is a collection of stream modules connected by streams, and each module consumes messages from input and produces result to output. To initialize a stream program, we have to firstly do the stream module definition and secondly connect different modules by streams. Take the stable diffusion, for example, the modules are clip module, UNet module, and VAE module. The stream connections between modules are as shown in the figure. Stream and stream module are the core concepts in NeuStream programming model. To be more specific, a stream is the data pathway between modules. A stream module, on the other hand, provides data processing functionality, and it is a schedulable entity and mainly consists of three parts. The parts are gather function. It selects a batch from the input stream. A compute function. It is a user-defined function that can perform actual execution on the batch messages. And the scatter function, it supports a customized rules to route message to multiple output streams. And modules are connected by streams. As explained, the stream program consists of two blocks, the stream modules definition and the stream modules interconnects. The figure illustrates the program of the stable diffusion. It first uses stream modules to define three phases: text encoder, backbone, and image decoder. Next, the program initializes streams and defines the model inference pipeline via module stream connection. The clip module transforms the input prompt into a latent stream, including text embedding and initial noisy latent, which is connected to the UNet module. The UNet module iteratively denoises the latent image messages in the latent stream and outputs the denoised latent messages. We decrease the iteration number of latent messages for each UNet execution and routed the denoised latent messages with the positive number of iterations back to the latent stream for UNet to execute the next iteration. Or we leave the others to the output stream, which is connected to the VAE decoder. The VAE decoder then will transform the latent message into the images. So let's say the above figure illustrates the architecture of our work NeuStream, which consists of four parts: a front end for receiving the user requests, and multiple stream workers for executing these requests, intra-scheduler inside each worker to determine the module-level batching policy, and an inter-scheduler across workers to determine the resource allocation inside our GPU pools. We can see that each worker is responsible for one module, and the front end will continuously send incoming requests to the first worker. Upon receiving a request message, the executor in the worker executes the gather, compute, and scatter function, iteration by iteration, and sending new messages to downstream workers based on the stream connections.
Hi, I'm Yuanqing Wang. Next, let's dive into the NeuStream system details. The goal for NeuStream is to maximize the system output, the number of served requests that meet their SLO requests per unit time. However, there are two challenges. First, the scheduling space becomes very large as we decompose the model into more schedulable modules. Second, the traditional overall SLO is not only difficult to meet, but also unreasonable due to the dynamic execution path. For the first challenge, we decouple scheduling into two levels, intra and inter-module. And for the second challenge, we assign SLO for each module. The request SLO is the sum of all the modules SLO. As long as the modules meet their respective partial SLO, the request SLO is guaranteed. This approach ensures independent batch scheduling across individual modules. We first focus on the intra-module section. During the system operation, Each worker holds a certain amount of computational resources and use an intramodule scheduler to determine the batch to be executed. Here is the procedural code of scheduling algorithm used. During the intramodule scheduling, the scheduler can decide which batch to execute based on the available computational resources, the SLO, and the requests in module's input stream. Larger batches can improve the throughput, but excessively large batches may violate the SLO, thereby reducing output. We first determine the upper limit for the batch size based on the module's partial SLO, and then iterate through all requests in the input stream. Requests with a negative budget are discarded in this loop. The budget refers to the surplus time accumulated in the previous modules when their completion time is earlier than the corresponding SLO. A request will be scheduled if its upstream SLO is satisfied, and the batch size does not exceed the limit after adding it. These two conditions work together to ensure that after the module completes execution, the request in the batch still satisfies the partial SLO in this step. This approach achieves higher throughput for specific module MI while allowing the GPU to operate at a high efficiency. Now let's dive into the intermodule section. Resource allocation decisions are made by intramodule scheduler. It uses virtual resources SPU as the unit of resource allocation, aiming to balance the maximum allowed output for each module under an appropriate resource allocation. Here is the procedural code of allocation algorithm used by intermodule scheduler. The algorithm first initialized all modules by assigning each module the minimum number of SPUs that satisfies the memory constraints on line 2. This step ensures that every module can be placed on the SPU with the memory limitations. When the map of SPUs to physical devices, the scheduler considers the module in descending order of their SPU allocation and maps the module's SPU to the device with the least available SPUs can still accommodate the module on line 6. Subsequently, based on the allocation, a latency function is derived. And at last, the SPUs are allocated to the module with the minimum normalized output. Finally, we will show some experiment results of NeuStream. We evaluate NeuStream on 3 representative types of modern model families: diffusion model, large language models, and multi-agent. For diffusion model, we use Clockwork as baseline, which supports request-level SLO-aware scheduling and dynamic batching. For large language models and multi-agent applications, we compare NeuStreams with VLM. The performance matrix is output, that is, the number of served requests that meet their SLO requirements per unit time. Similar to prior work such as AlphaServe, we generate the request arrival time using gamma process, which is parameterized by rate and coefficient of variance, or CV. By scaling the rate and CV, we can control the workload's rate and burstness, respectively. For diffusion models, we use 2 types of image sizes and use a uniform iteration distribution over the recommended range, such as 30 to 50 for stable diffusion. For large language models, we use LM6chat 1 million, a large-scale dataset containing real-world conversations with 25 SOTA LLMs. And for multi-agent, we use Matplotlib consisting of complex data visualization problems. This figure shows the result of serving distribution models with 2056 times 2056 image size on RTX 4090 GPU. In each row, we change 1 parameter. In the first row, we change the number of requests per second. The second row is the CV of the arriving interval, and SLO for the third row, to see how workload variation affects the performance of each serving system. And each column represents 1 model. In the first row, NeuStream provides significantly higher output due to batching more requests on the module level, up to 4.3 times at 4 requests per second in the DITS-2 model. In the second row, the traffic becomes more bursty with a higher CV, which increases the possibility of SLO violation. resulting in quick output reduction in clock work. By contrast, the more bursty increases the batching opportunities in NeuStream, which alleviates the negative effects of high bursty requests. NeuStream outperforms clockwork by up to 4 times on DITS at high CVF4. We see that even SL is only in the third row, SL scale equals 1 means the latency requirement is the single request inference latency. As SL scale increases, the latency requirement becomes looser. We see that even SL is only slightly larger than the model inference time, NeuStream gets a much higher throughput due to module-level batching, up to 3.1 times at a small SL scale, 1.2. To fully understand NeuStream's baseline benefits on batching, we plot the running batch size on DIT model for DITS-2 along the time. On average, the batch size of NeuStream is 5.35 times larger than clockwork due to efficiently batching requests that arrives at different times, require different numbers of iterations, or start with different number of iterations. The figure on the right increases the batching opportunity of clockwork by setting the same number of iterations for each request, that is, disabling the third case. We see that NeuStream still has a larger batch size, 1.67 times larger on average. This figure shows the result of serving LLM on NVIDIA H100 GPU. The first row shows that as the request load increases, VM output starts to decrease significantly because the decode resource starvation and preview congestion. In contrast, NeuStream is the SLO aware and balances the resource provision across the modules. For OPT 13 billion, NeuStream outperforms VRM by 5.1 times at 8 requests per second. As shown in the second and third row, NeuStream performs better to handle more burstiness and that aggravates the resource contention. For example, for OPT 16.6 billion, 1.5 times at CVF4 and 6.7 times at SL scale of 1.6. This figure shows the normalized good path of each module on RTX 6000 ADA for different LLMs, and we can see that NeuStream's allocation ensures a balanced processing speed between stages, since our inter-module scheduling explicitly allocates SPUs to maximize the minimum module normalized good put. And the results for multi-agent are similar to those of LLM. This slide shows the profile cost and latency breakdown in NeuStream. Profiling the latency function is a one-time preprocessing stage, which is negligible compared to the subsequent long serving time. We also make a latency breakdown on the request in the NeuStream and find that scheduling only accounts for less than 2% of the latency in stable diffusion and LLM, and 5.3% in more complex multi-agent tasks. In summary, NeuStream addressed the efficiencies of serving modern DNN applications with dynamic execution patterns on GPUs. By introducing the concept of streams and stream modules, NeuStream enables continuous data flow execution model that effectively maximize GPU utilization while meeting stringent latency SLOs. Thank you.